viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani from Department of Computer Science, Aryabat College, University of Delhi. So in our last lecture we have kind of begun with a new and important data structure which is mostly used in terms of or in application scenarios of pattern matching, and the data structure is titled as tries. So what is the agenda for today's lecture? We will be looking into some basic operations like insertion and searching on tries, and we will be also looking that how this try is going to kind of help in case of word matching. So let us take a quick recap of what is try, and then we will begin with the operation for the try. So try basically a tree data structure in which the kind of elements are arranged after following some rules, and the structure of nodes is arranged in a particular way so that the words and strings can be retrieved from this try by traversing down a particular branch path. And we have seen this try which is being shown on the screen as an example in the last lecture, and this is a standard try for the set of strings. 8 elements in this set of strings, capital S have been taken: bear, bell, bit, bull, buy, sell, stock, stop. So one it is having kind of 2 subtrees. One subtree is starting from B, another subtree is starting from S, and then kind of these subtrees are representing each branch of these subtrees is representing one string or one element of the set S. So for example, the first branch or the leftmost branch is representing B, E, A, R. Then the second one is representing B, E, L, L with B and E as the common portion. Similarly, if you can see the rightmost branch, it is having 3 portions in common or 3 characters in common. One is S, another one is T, and the kind of next one is O. So S, T and O are common, and C and K are going with a different branch, and so is P for stop. So this is actually a standard try that we have seen in our previous lecture. Now what are the basic operations which we are going to which can be performed on this try? So like other data structure or like other tree data structures, the basic operations are insertion, searching and deletion of a node. So we will be looking into insertion of a node first, but before going into insertion of node, we need to keep in our mind some very important points that the so these points are: the first says every letter of the word which is to be inserted, or we can say input key, is inserted as an individual in the try node. Because we are talking about the standard tries, there is nothing kind of that each node or any node is storing 2 characters at a time. So one letter of the input key is inserted as an individual in the try node, because we are talking about a standard tries. So one node storing 2 letters is possible, but not in standard tries. That will be kind of a compressed try that we will look in our upcoming lectures. And please note that the children point to the next level of the tries node. So from one try node to from one children to another children, you have covered one level of try node, and the key character array act as an index of children. Now what do you mean by this? The key character array act as an index of children. You please hold with this particular line. I will explain this at the end of this lecture with the help of a particular figure. So how are we going to kind of insert any letter if we want? So let us see that with the help of a figure. So initially we have an empty try which is just having a root node, and the input word which we want to insert is AND, A and D. So, from root node there starts a branch A, then it is going down to N, and then it is going down to D. So, here you can kind of enclose the letter D in the square or rectangular box also, just to show that this is the kind of leaf. Now, for example, the second stage in this figure says that we actually want to kind of insert another input word which is ent. Now, what is the common portion between ent and end? That is A and N. So, A and N we will not be repeating for ent, rather than we will split out a branch from N. One branch of N is already going to towards the letter D, and now the second branch will go to the letter T as it is shown in the figure. So, if you try to understand the concept of insertion of this insertion of nodes, it is kind of I can say very simple, which says that if the present node already has a reference to the present letter, we need to set the present node to that reference node, otherwise create a new node. What does it mean? So, for example, when we are inserting AND, so A and N are already kind of present there. So, we need not to repeat them, we will just be kind of using this A and N, and then we will making our branches forward or creating our branches forward for this letter T. So, this says that if the present node already has a reference to the present letter, so present node is AND, A and T, and the present letters are present node is R, A and D, and the present letters are A and N. So, that means there is a reference. So, we will be kind of setting the present node to that reference node. Otherwise, we need to create a new node, set the letter to be equals to the present letter, and even start the present node with this new node. So, for example, in this figure, if I am going to insert one more input word, let us say cat. So, cat begins from C, so there is no common reference kind of thing. So, there is a branch, there will be a branch for C which will start from the root node itself. So, now there will be two branches, one which is going towards A, another one which will go towards the C, and in this way we keep on kind of building our data structure, and the character length determines the depth of the trie. So, for example, in our previous example which we took for 8 strings, 5 from B and kind of 3 from beginning from S, the largest one was stock, which is of 5 letters. So, the depth of the trie will be maximum 5 in that particular case. So, here that is why we are saying that the character length determines the depth of the trie. Now, this was basically an operation which is the most basic operation of insertion. Now, coming to, and I have told you only the concept of this insertion operation, we have not yet we have not seen the algorithm corresponding to this insertion operation. Now, looking for the another basic operation which is of searching a node in trie. Now, that is very similar to insertion operation, and like other data structure, that is kind of sure that while performing an insertion operation, you need to first search the position, or you need to search through some nodes in order to determine the exact position of the node which is to be inserted. So, we can say that for up to an extent this searching a node in try, and it is actually similar to the insertion operation. And the search operation basically, as you are aware, is used to search a particular key in try. Now, in order to look for a particular key in try, what we need to do? The idea is very simple. You only need to compare the characters and move down, that is it. Compare the character, move down, compare the character, move down till a particular limit. Now, what is that limit? So, the search will terminate either due to end of the string or maybe due to the lack of key in the try. So, that means either there is no such key which is being looked for, or there is kind of end of the string, which that means we have already we can say found out or find our node. So, for this searching operation, we need to start at the root node, which is the blank node, and traverse the try based on the character of the word you are looking for or you are searching for. And for each character, we need to follow the corresponding branch in the try, and if the branch does not exist, that means the word is not present in the try. So, let us take an example. So, here is the screen which is showing the example which we have taken for insertion. Now, in this final tree, which is represented with the help of two strings, one is A and D and another one is A and T. For example, I am looking for the word A and S. So, it will start from the root node, A is there. So, A it will kind of take, then N is also a match from what I am looking for, which is A and S, and then after N there should be S. So, if S is not available, so that means the result is that this A and S key is not available. Now, for example, I am looking for AND. So, again very simple, start from A, go to N, and then you have kind of the letter T. So, searching is kind of very simple. What you need to do, as I told you, that you will compare the character, move down, compare the character, move down, and at one point the search will terminate either due to the end of the string or the lack of the key in the try. That means that key is not available, or that key is available, you kind of perfectly traced that down and you are coming to the end of a string, as in case of AND we just did. So, we need to traverse the try based on the characters of the word which you are looking for. For each character, we need to follow the path which is going in the down direction, and if the branch does not exist, that means the word is not present in the try. Now, in order to kind of terminate the search very cleanly, one particular thing we can do in pre-processing while kind of creating or while inserting the input words, that is setting a flag, setting a word and flag, that can be done. So, if we reach the end of the word and the word and flag is set to 1, the word has been found, and if you reach the end of the word and the word and flag is 0, that means the word is not present in the try, even though it shares a prefix with the existing word. So, for example, in case of A and S, if I am looking for A and S, the two letter prefix which is common is A and N. But even after following that path of A and N, I will not land up with a successful search because S is not present. So, that means what will be the conclusion, that word and flag is 0, and I have already kind of reached at the end of the word. Word is not present in the try, even though it is sharing a kind of prefix. And what will be the time complexity and the kind of space complexity when I am talking about the searching thing that we will also look into, but please recall the first lecture which says why this trie is being used, because this is going to give you a compromised situation between the time complexity and the space usage. So, time complexity here in case of searching is going to be order of number of words multiplied by maximum length of the word. So, for example, maximum length of the word in our first example which we seen at the time of understanding the concept of trie was 5, that was stock, and the number of words. So, for example, that is 8, but as I am talking about an asymptotic notation, we should not go into these concrete figures, that will not make any sense. Auxiliary space, if I am talking about how much auxiliary space it is going to take. So, the auxiliary space is also kind of similar, which is order of number of words into max length of words. So, this is the kind of I can say details of time complexity and the space complexity or auxiliary space requirement in case of searching. Let us see one more example of searching which is kind of giving you a successful result. So, we have a root node and we have a trie. We are looking for a string DAD, which is DAD, and we have A and D, we have A and T, and the third string is DAD which are looking for, and it is being followed or it is being represented by the right hand or the right subtree. So, root node, it is going to give you D, then A, and then D again. So, starting from the root node you go to D, then you traverse down the path to A, and then you traverse down the path to D. So, either here you can check if the word end is equals to true with the help of a word end flag, or kind of here you can represent it with the help of a square or the rectangle, the last node of D I am talking about. But at the time of implementation, if you are looking for then you need to check this with the help of a flag, that whether this word and is true or not false, then only true or false, then only you will be able to kind of result in either a successful search or maybe an kind of unsuccessful search. Now, while implementing the insert and search operations in trie data structure, I am giving you so just a hint of the programming, that if we actually want to implement insert and search operation in this trie data structure, how are we going to kind of deal with it? So, first we need to create a root node with the help of a trie node constructor. Trie node constructor has been created initially here, initially or even after your root node is empty. Then in order to store a collection of strings that are to be kind of inserted in the trie, we can take a vector of strings, and insertion of all the strings in the trie can be can take place with the help of a function which may be named as insert key, or whatever the suitable title of the function or suitable name of the function you may kind of guess, and the search strings searching strings will take place with the help of another function assuming search key as the name. And within this insert key we have this vector of strings, and we will take one string at a time, and then we will keep on inserting the strings inside that trie which is having one particular constructor as of now representing the root node, and that is the empty root node. Now, when at the beginning of the trie lecture or in the previous lecture, when we were looking into the standard trie, I told you, and in this lecture also I have kind of repeated that fact, that this trie is actually a kind of compromise between the space and the time complexity. Now, how that is going to be a compromise, So a standard trie uses order n space, and it is going to support the basic operation. Which basic operations I am talking about? What all are these basic operations? Search, insertion and deletion time. So searching, insertion and deletion will take or the time complexity of searching, insertion and deletion is order of d multiplied by m. Now what is this d and what is this m? And this order n is the space which is being kind of required by the standard trie. So where, if you can see, the n is the total size of the strings in S. So considering my previous example of beer, bill, bell, bid and so on and so forth, 8 was the size of the strings because there were 8 strings in S. M is the size of the string parameter of the operation. So the maximum size in that particular example was stock, which is of 5, and D is the size of the alphabet. Now what is the size of the alphabet in case of your English alphabet is just kind of 26 letters, and I have already told you that if I am looking into or I am kind of representing a trie using or I am creating a trie for the binary strings, then it is going to be kind of the size of the alphabet is 2. And now for example, let us take example of one more scenario that we are kind of making the trie of DNS sequences. So DNS sequence is always made from 4 letters, one is A, another one is T, then C and G. So the size of the alphabet for DNS sequences is 4, the size of the alphabet for binary strings is 2, whereas the size of the alphabet for your kind of English alphabet is obviously 26. So the search, insertion and deletion operation will take order dm, and a standard trie is going to use an order n space. Now at the beginning of the lecture, if you remember, I have told you that you need to kind of hold down a particular fact. What was the fact? The fact was the key character array acts as an index of the children. Now let us see the meaning of that particular sentence in terms of tries, that the key character array acts as an index of children. So this concept comes up when actually we are going to look for an application of word matching with the help of a trie. Normally we insert the words of the text into a trie, and each leaf stores the occurrences of the associated value in the text. Now this is actually what you can see on the in the figure is actually a different kind of a trie, or I can say actual representation of trie. So in this figure you can also see one particular array of strings, or I can say there is a complete text which says that see a beer, sell the stock, see a bull, buy the stock, and the next 2 lines are kind of this is basically a text, and this text is being arranged in the form of an array, and that array is actually kind of being provided as an being provided with an index starting from 0, and it is ending at a particular number which is 88. So starting from 0, 88, so 89 characters are there, and when we actually want to represent these 89 characters with the help of a trie, not 89 characters but the kind of strings. What are the strings? So C is a string, A is a string, then we have beer, that is a string, sell is a string, stock is a string. Now when we talk about this pattern matching, or when we talk about these language processing things, one thing which we need to kind of do always is we can say avoiding these stop words. So for example, I am talking about A. So, A is not being represented here in this try, or for example, the is also not being kind of represented. Now, what is happening here? So, at a particular kind of node, this try starts from an empty node, and at a particular node or at the, I can say, leaf, you will find some indexes in the figure. Now, what are those indexes? Those indexes actually represents the position of that particular word in the text. So, for example, if you follow the leftmost branch, you will have a particular number, let us say 6. So, that particular the term beer, that you are going to find starting from the position 6, and in this way when we kind of put some indexes at the end of the strings in the try, then we are going to have kind of, we can say, a very fast kind of searching. And this was actually the meaning of that sentence. That what was the sentence? Let me recall. The sentence was about that the key character array, that was the key that's the key character array which is being represented on the screen, acts as an index of children, and index of children is being kind of written at the bottom. So, in this way word matching takes place with the help of a try. So, in this lecture what we have covered, with a quick recap of try, we started with the insertion operation. We tried to look into the how this insertion operation is going to take place. Then we came up to the search operation. We looked into a couple of examples of search operation, and then finally we also kind of looked into that how a particular application for which your try is famous, and that application is of, I can say, a word matching or a particular pattern matching is going to take place, because that array acts as the kind of indexes of children, which is being given here in the last figure. So, here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this lecture. I will see you in the next one. Till then, take care. Goodbye.